Okay, guys, welcome to Wednesday's lecture. Thank you for joining us on YouTube if you're watching later. Just a few administrative announcements. Assignment 3 is for marks, so you should be starting to work on that when you can. I was taking a look at the schedule kind of on the weekend in and around when you guys were doing your midterm, and I pushed the due date back for assignment 3 by, I think, a day or two. I can't remember what the old due date was, but I think at least a day, because I realized we would only be finishing momentum today, and I wanted to give you, a little bit more time to work on those problems. So if you'll notice this week here, you can see up on the screen that I'm sharing, we're sitting here on Wednesday the 27th, and we don't, technically within this week, we do not have the assignment 3 due. If you scroll down to June, later on, you see on June 1st, Monday, June 1st, of course we've got a lecture that day as well, but Monday, June 1st is now the new due date for assignment 3. And this is to give students a little bit more time after finishing momentum to work on those problems. Now, I will say the previous unit of energy is a really important concept in physics. Momentum is arguably a bigger concept in physics. And you'll notice that when you're doing these problems, especially after today's lecture, you'll notice this, a lot of momentum questions are kind of entwined with the conservation of energy. And we're going to talk about that today a little bit when we do different types of collisions with inelastic and elastic collisions. So, sometimes you kind of have to use some energy concepts as well when you're doing momentum questions. So you will need both of them on assignment 3. If you're finding yourself gravitating, no pun intended, gravitating toward starting the question with some sort of conservation of energy, that's probably correct, in all honesty, depending on the question, but it's probably correct. And then kind of halfway through the question, you might have to, switch to momentum and then switch back to finish the question with energy. So if you find yourself doing that, please be reassured that that's a very common thing when you do momentum questions. The only other administrative thing I'm going to mention is that the results of the poll are in for the syllabus amendment, and it looks like there was over 80% of you have agreed to the proposed amendment. So I will be reaching out to the affected students, today and tomorrow, and there's only a small few of them. I think I could probably count on one hand or 1.5 hands how many students are affected. So I'll reach out to them individually, and you'll obviously know who you are when I reach out to you. And if you don't get an email from me, then that means you have not been identified as being in that category. So anyway, I thank you all for participating in that democratic vote. It is, I know this is not like government or anything, but it's still your class as well, so it's good that we're all kind of partaking in the democratic process of voting. Okay, without further ado, I think we can switch on over to the lecture notes. So we left off yesterday with talking about, introducing the idea of momentum and how it is the quantity that represents how much motion something has. Dynamics talked about what causes the motion, right? It's a force. Kinematics talks about assuming the motion exists, where is it going to go? Energy was the band-aid that sort of got around a variable force. But we up until then, we had not discussed motion itself. What caused it? Fine. Where is it going to go? Fine. But how much motion does something have? And that was a missing piece of the puzzle. You may not even realize it was a missing piece of the puzzle, but hopefully now you can kind of start thinking about, when two objects are moving at the same speed, that doesn't necessarily mean they have the same amount of motion, right? Because it's mass times velocity. So we did a bunch of examples yesterday in one dimension, just to get your feet wet, so to speak, with the vector nature of momentum. And we talked about how the conservation of momentum predicts that no matter what happens within a closed system, the total amount of momentum remains constant, which means things can share momentum, can transfer their momentum from one object to another object, but in a closed system, the total momentum in that system must remain constant. And that is a fairly simple thing to think about, but it has some pretty profound implications. And we talked a little bit about kind of how we can use that to map our universe. Even something less philosophical than the universe, we can talk about how two objects are initially at rest with no momentum, and how, an explosion of sorts, like, firing a bullet out of a gun, can cause a recoil, right? That's a result of conservation of momentum as well. All of these things were in one dimension, of course. And just like we did with forces, we are now going to talk about momentum in multiple dimensions, because it is a vector, and that is something we have to review. So I will give you a bit of a hint. Nothing, and I kind of mentioned this yesterday, nothing really changes here between one dimension and two-dimensional momentum, and especially compared to when we did dynamics. Dynamics, when we did two-dimensional forces instead of one-dimensional forces, all we did was we assigned a coordinate system, like, X and Y, or ramp and perpendicular to ramp. And then we just did components, right? We just did F net X and then F net Y. So that's all we're going to be doing here. So here is, and of course, there we go. Here's foreshadowing. It says momentum in two directions, and you see kind of a picture of, objects colliding over here. What's happening? I do not know what's happening. There we go. So yeah, you see, come on. I do not know. Okay, well, technology, gotta love it. You see over where the balls are colliding on the diagram over on the left, there's two objects colliding and they ricochet off at angles. And then there's a chart here on the right-hand side. And at the moment, this is gonna seem confusing to you because, there's no context for it, but please keep this slide in sort of the back of your memory while we sort of develop the next example here. And we're going to conclude by showing you kind of where this chart came from. The simplest of two-dimensional cases would be something like example 12 in the attached notes or the typed lecture notes. So that's what this is here. The situation that is depicted on the slide above says a billiard ball, like if you play pool, like in a bar or something, a billiard ball is traveling at a speed v1 towards another identical billiard ball that is stationary. The two balls strike each other and they rebound at different directions. So what makes this two-dimensional is, although the initial amount of motion is in the x direction, after the collision, one ball kind of goes off on an angle and the other ball goes off on a different angle. So after the fact, because of the angled ricochets, we now have to branch out into two-dimensional space instead of one-dimensional space. So that's kind of the premise here. And I do want to emphasize something, that one of the objects is at rest. Okay, that's the simplest two-dimensional case, when only one object is moving and the second object is at rest. Okay, obviously in real life, multiple objects are moving and colliding, right? So we're going to start with the simplest of objects and go from there. So as I mentioned before, if you're studying momentum, it's really no different than dynamics. First, you start with a bit of a diagram. So we know that this object is coming in horizontally with speed v1, and it strikes, or it's headed toward a stationary object mass 2. And then after the collision, we say v1 prime is kind of up over here, and maybe it ricochets off at an angle. If you've ever played pool before, you'll kind of know what I mean. When two pool balls hit each other, they kind of ricochet off at different angles. And object 2 will come off maybe at a different angle, kind of like this. Okay, so this is sort of the before, and this is the after. Well, just because we're in two dimensions doesn't mean our approach is any different, as you recall from dynamics. So once you've established that this is in fact a momentum's question, and the key here to know that it's a momentum question is that there's a collision involved. You know, normally with forces, the key is when we're talking about a force, you know, a free body diagram, F net equals ma. Energy is typically when the phrasing in the problem requires you to sort of, you know, when a bunch of events happen and the middle stuff doesn't really matter, all you care about is kind of what happens at the end. That would be energy when things change in the middle. And momentum, a pretty clear sign that you need momentum is when there's some sort of collision that takes place. So I know this is part of the momentum lecture, so it's kind of obvious that that momentum is kind of needed. But again, you know, on the next test, for instance, we're not going to be holding your hand telling you solve this using momentum. So if you want to develop some intuition as to an analysis approach, if there's a collision involved, you're needing momentum. So we start with P total equals P total prime, but of course, these momentums are a vector. Now, overall, even though beforehand there is no 2 dimensions, it's only 1 dimension beforehand, ultimately, overall, between the before and the after, there's 2 dimensions that need to be analyzed. So what I would recommend doing is I would recommend staying organized and drawing some sort of a chart. Now, if you've taken grade 12 physics and you kind of have your own way of doing this, you know, go nuts. I'm not going to stop you. But if you're new to this, or let's say you don't really remember grade 12 physics, or you struggled in grade 12 physics with this, I highly recommend a chart. And what we're going to do is we're going to draw 1 row in this chart for each object before the collision and 1 row for each object after the collision. So the first row, I'm going to draw a picture of the object and the direction of its momentum. So beforehand, it was traveling to the right. And how much of the momentum is in the x direction? Well, I would say all of it. So m1, v1 is in the x direction. And how much of this vector is in the y direction? Well, this is why you draw a picture. If you draw a picture, you can visually see that none of it is in the y direction. So what I'm doing with this chart is I'm breaking the momentum vectors into their components. The next row in the chart is mass 2. I should really label this mass 1, mass 2. Now, before the collision, mass 2 isn't moving at all. So none of its momentum is in the x, and none of its momentum is in the y. Now, after the collision, I'm going to draw a double line here to indicate, or maybe even a triple line to indicate that the following rows are for a different scenario. After the collision, we know that object 1, according to our diagram that we drew above, is kind of going off up here at some sort of angle theta 1. So looking at this, how much of this momentum is in the x direction? Well, we have m1 v1 cos theta 1 in the x direction. And how much of this momentum is in the y direction? m1 v1 sine theta 1 is in the y direction. And lastly, we have mass 2. And according to our picture, its momentum comes down like this at an angle theta 2. Oh, sorry, I should really say m1 v1 prime. m1 v1 prime. It's not the initial speed, it's the speed after the collision. Okay, and then momentum 2, how much of its momentum is in the x direction? m2 v2 prime cos theta 2. And in the y direction, it's actually pointing down. So it's negative m2 v2 prime sine theta 2. And there you go. So this is where that chart comes from in that slide above. And really, like I said before, this chart isn't, like it's not the be all and end all. It's, if you have another way to set up your equations and your quantities, by all means, go for it. However, I like this chart because what it does is this summarizes all momentum before the collision. And these summarize the momentums after the collision. So conservation of momentum still is true. And as I've mentioned a few times now, like with dynamics as well, if we have two dimensions, all we simply do is we perform conservation of momentum both in the x direction separately from the y direction. And this is where this sort of notion of independence comes in again. This is why your coordinate systems have to be perpendicular to one another. And if you need to refresh independence, you can go back and look at those lecture notes on coordinate systems and independence, because that's kind of where that comes in. But if you can get over that hump and just kind of understand the independence, we can jump right to it. I would say here that momentum total in the x direction has to equal momentum total in the x direction prime. Well, that simply means that these quantities have to equal these quantities, right? The total momentum in the x direction before the collision has to equal the total momentum in the x direction after the collision. So writing that down, this chart helps you actually come up with your conservation equations. Here I can see I'm going to have m1 v1 equals m1 v1 prime cos theta 1, and then p total in the y direction is going to equal p total in the y direction prime. And that gets me, that gets me 0 equals m1 v1 prime sine theta 1 minus m2 v2 prime sine theta 2. There you go. So these are our two starting equations for this setup. And notice here how the only assumption I made was that the initial speed of object 2 was 0. I did not, this question did not assume that we had, you know, m1, m2, and theta 1 and find the other ones. Right, this setup was just, okay, let's just figure out the physics of the situation. So really, this is a general setup. Any two-dimensional problem you're doing is going to like have almost exactly this setup, almost perfectly this setup. So this is kind of showing you how flexible this sort of analysis approach is. It doesn't really matter what two-dimensional momentum problem you're trying to tackle. It's really the same setup. Once you get your final equations, they're mostly going to be like this. I mean, depending on the exact geometry, maybe m1 goes down and m2 goes up. So, you know, there might be a negative sign for, there might be a negative sign here and a positive sign here. Like it kind of depends on the exact problem, but for the most part, it's pretty much the same setup. So if you look at the slide above, that's where these equations came from. It's, you know, that's where the chart comes from, and that's how we use the chart to obtain those equations. Now, one thing I want to point out here is how many variables are there? How many variables are there? Sorry for the messy handwriting. That should be an R. That's not much better. So there is m1, m2, v1, theta 1, theta 2, v1 prime, v2 prime. Okay, so there's 7 variables there. Now, that's not a small number of variables. Now, how many equations do we have? We only have 2 equations. So let me change colors here. But we only have 2 equations. So if you only have 2 equations, then in order to solve this system, we have to give you all of the variables except two, right? The maximum number of unknowns you're allowed to have with two equations is two unknowns. So this means that that's not useful. We must give you 5 out of the 7 variables in a problem in some capacity. Now, they could just be explicitly said that theta 1 equals 2, or whatever, theta 2 equals 30, or they could be sort of implied. Implied meaning we could say somewhere in the question like, oh, and mass 1 ricochets off northward. Well, that's not explicitly saying theta equals whatever, but the words mass 1 ricochets northwards kind of gives you the direction of theta 1 implicitly that way. So in some sense, we have to give you 5 of the 7 variables. So even though there's kind of a lot of combinations, at the end of the day, your equations are always going to be the 2 equations here that are boxed in red. However, they are really they're pretty much the same starting equation. We're just giving you different combinations of 5 variables we give you and asking you for the 2 that are unknown. So that's all there really is. I'm trying to explain to you that although it might seem daunting and it might seem like a lot of different variations and permutations, they all pretty much stem from the same 2 equations. So they're really not that bad. Okay, so I think we can do, oops, what's happening? I think we can do an example now. So let's insert some space here. Okay, so here's an example. A grenade of mass 1.2, okay, so words. I'm just gonna start writing variable quantities here. Okay, so a grenade of mass 1.2 kilograms is at rest, all right, on a smooth, frictionless surface when it suddenly explodes into 3 pieces, okay? So I should say mass total here, I guess, because it's going to be splitting into pieces. The first piece is what, 0.5 kilograms according to the question, flies off horizontally to the north at 3 meters per second. So V1 prime is 3 meters per second north. And a second object, or a second chunk of object of mass 0.3 kilograms flies off southwest at 4 meters per second. So this is going to be southwest. What is the velocity of the third piece? Well, M3 is going to be mass total minus mass 1 minus mass 2. So that's easy. And we're wanting to know the velocity and direction of that one, of the third piece. Okay, so again, this is daunting. There's 3 objects instead of 2. The previous question I said had 2 objects. I'll show you that it's really not that much different doing the analysis with 3 objects, especially when you use the chart method. It's downright algorithmic. So I would say let's start with a picture. So we have a grenade that is sort of broken up into 3 pieces. Initially, it's at rest, and one mass flies straight upwards, M1. One mass flies southwest. Now, in our head, we kind of know conservation of energy. Well, actually, let me redraw a sort of flake here. There we go. Mass 2. I'm going to draw little arrows to indicate that it's kind of flying away. Now, we know conservation of energy in the back of our head exists, right? So looking at this diagram, we have an object that's traveling kind of up, we have an object that's traveling down and to the left. So all of these vectors have to balance out to 0 because the total momentum beforehand was 0. So that tells me the third object probably has to kind of come out like this. Now, it definitely has to be traveling to the right because mass 2 is traveling to the left. So something has to balance out left with right. Now, I don't know if it's pointing a little bit up or a little bit down. So we can figure that out as we go. And that's what's a good thing about the chart, to be completely honest. So we can now draw our chart. So X, Y. The initial object, I'll just shade it in, mass total, has no momentum in the X and no momentum in the Y. So my total momentum before the collision is 0. So I only have one object before the collision. And now I'm going to draw some more lines to indicate that it's after. So after the collision, I have mass 1, give myself more room. Mass 1, there we go. Mass 1 is traveling upwards, straight northwards at v1 prime. So how much of this vector is in the x direction? Absolutely none of it. How much of it is in the y direction? All of it. All right. Next one, mass 2. Well, we know mass 2 is aiming southwest. So southwest means we have an angle of 45 degrees. And you can label this angle either from the south or from the west because 45 is literally dead smack in the middle. So you can label it on either side, it wouldn't really matter. So how much of this is in the x direction? Well, it's pointing left. So because it's pointing left, I'm going to put a negative sign there. And it's pointing M2, V2 prime, sine 45 in the leftward direction, so it's negative. And how much is it pointing in the y direction? Well, it's pointing in the negative y direction, so I'm going to put a negative there. And it's pointing M2, V2 prime, cos 45. Now, you might be picking up on this, sine of 45 and cos 45 are equal to each other because it's 45. That is a special triangle. That's not the point. I mean, the question happens to be at 45. It could have said 46, 47, 50, 55. So just always draw a diagram and keep your head on your shoulders is, I guess what I'm trying to say here. Don't pretend that 45 is just, going to be a thing all the time. And then lastly, we have mass 3. So we know from intuition, and someone was asking yesterday about intuition and I think the question was, how do you prevent your intuition from coming into solving physics? And my answer was, it's the opposite. You want your intuition when you're solving physics questions. So, this is why you draw a diagram ahead of time. My intuition tells me that the direction has to be in some capacity to the right. It has to be, because it has to balance out the left. For instance, you can see, I'm just trying to change color here. You can see that beforehand, there is nothing in the x direction. And
wow, I'm so proud of myself. I did this assignment.
Can you mute yourself, please? Thank you. You can see ahead of time that there's no momentum in the x direction. And over here, there is no momentum in the x direction. So if we have a negative momentum here, then we know that this one has to be in the rightward direction. So this one's going to have to be positive. We know that ahead of time from our intuition. Oops. So how much momentum are we going to have in the well, the x direction? In some capacity, we're going to have m3 v3 prime, but we don't know if it's going to be tilted up or down. That's the thing, because mass 1 is heading upward, mass 2 is heading downward. So to balance out, we don't know if mass 1 already balances mass 2 for the vertical directions. We have no idea. So we are going to just draw this. I'm going to just make an executive decision here. I'm going to assume that it's a little bit upward. I could be wrong. Let's assume it's upward a little bit. So in the x direction, this is going to be cos theta 3. And if I'm assuming it's a little bit upward, then I'm going to make this positive. M3 V3 prime. That's going to be a sine theta 3. All right, so, and we have now 3 rows for after the collision. Insert some more space. All right, so now we need to set up our equations. So we're going to do momentum total in the x direction equals momentum total x direction prime. So we see before the collision, there's no momentum in the x direction. After the collision, there is none from object 1, minus m2 v2 prime sine 45 plus m3 v3 prime cos theta 3. Yeah, we don't know theta 3. And that's it for the x direction. And then for the y direction, we do the same. So before, there's no momentum in the y direction. Afterwards, there is m1 v1 prime minus m2 v2 prime cos 45 and m3 v3 sine theta 3. All right, now we just have to kind of take inventory of what variables we have and which variables we need. So in red here, m2, yes, I have m2. v2 prime, yes, I have v2 prime. m3, yes, I have m3. v3 prime, no. Cos 3, no. Okay. m1, yes. v1, yes. m2, yes. v2 prime, yes. m3, yes. So the things we do not have are the magnitude of v3 prime and cos theta 3. So 2 equations and 2 unknowns. So that's what we're solving for here. Need to insert some more space. All right. Now, you will find that it's actually impossible to eliminate theta in this case, because theta appears both in a sine and a cos in the 2 equations. So eliminating theta is going to be difficult to do. So you could first maybe eliminate v3 prime and then solve for theta using like inverse tan or something like that. Another way to do it, and this is just sort of a trick of the trade, is you can say this represents the momentum of object 3 in the x direction after, and you can say this represents the momentum in the y direction of object 3 after. And you can just solve for the momentum components themselves, and then you can find the angle just by doing inverse Pythagorean theorem that way. So you can do either one. You can either eliminate v3 first and explicitly solve for theta that way, or you can sort of lump all of those terms together. It's a little bit easier to do if I lump the terms together, so that's the way I'm going to proceed. So I'm going to change to black ink. All right, so moving through this, rearranging, I'm going to get m2 v2 prime sine 45 equals momentum in the x direction of object 3 after the collision. So there you go. We have that number. And if you go through, I think you're going to end up getting let's see here. Well, whatever that number is. And then in the y direction, if we clean this up a little bit, momentum in the y direction of object 3 prime after the collision is going to be equal to m2 v2 prime cos 45 minus m1 v1 prime. There you go. So you can actually compute what these values are going to be, and you can kind of plug them all in. And then you can say the momentum of object 3 after the collision is going to be, or I should say the magnitude of the momentum of object 3 after the collision is going to be the Pythagorean sum of its components. And when you do that, when you add them all up and plug in all your values, like for instance, let me just change it to red quickly. We have M2, we have V2, we have M2, we have V2, we have M1, we have V1. So when you plug in all your values, I think you're going to end up getting something like 1.1 kilogram meters per second. And now you're left to find the angle of vector momentum 3 prime. And that's solved by doing theta equals arctan of the momentum in the y direction over the momentum in the x direction. And if you do that, I think you're going to get something like east 37 degrees south. So the fact that it's south means, let me just do this in a different color, means that my assumption of, oh, it's getting jittery, of object 3 traveling upwards was false. And you'll notice this because this ends up being a negative value. When you plug in all your numbers there, you're going to end up getting a negative value. So that tells you that when I assumed in my chart here, when I assumed that it was pointed upwards, I was wrong with that assumption. So mathematically, if you get a negative there, it means it's negative up. And negative up means down, or I guess in this case, south. So your final answer should be therefore momentum 3 prime after the collision is 1.1 kilogram meter per second east 37 degrees south. So I would encourage you at some point in time to go back and plug in all your values for M2 and V2 prime and sine 45 and all that other stuff, and see if you can replicate 1.1 and the angle of 37 degrees. And if you can, then that's great. You're well on your way. Okay, now moving on. So as I mentioned before, a dead giveaway for momentum being the thing that you need to analyze a problem is when there's a collision present. And when there's a collision present, well, to the untrained eye, you might seem all collisions are the same, but to a trained eye, there's actually three different kinds of collisions, but there's two categories of collision. So that's what we're going to be talking about. The first category of collision is called an inelastic collision. So like I've mentioned before, physicists, we are quite simple when it comes to naming things. So there's a logic behind the word inelastic. Why do we use the root word elastic? Well, if you picture a spring or a rubber band, if you elongate a spring or you elongate a rubber band or an elastic band and you let go, what's going to happen is there's a force within that spring or a force within that elastic band that tries to pull back the object into the original shape, meaning it's an elastic material, meaning if you deform it in any way and then you let it go, it will retain its original shape, as does an elastic band. If you deform an elastic band's shape and let go, you know, after it snaps or whatever, or, you know, you launched across the room, after that, it will retain its original shape. So an inelastic collision is something that, you know, after the collision and, you know, after you've deformed an object's shape, it stays deformed. It does not return to the original shape that it used to be. So when you're approaching physics questions and you're trying to figure out, okay, is it elastic? Is it not elastic? You have to ask yourself, is the mass the same as what it was before the collision? Or is the mass a different shape after the collision, or in a different form after the collision? If it's in a different form after the collision, then it's not elastic. You've deformed it and it stayed deformed. So that's the logic behind the wording of the word inelastic. Now, from a student perspective, you had better pray that inelastic questions are asked on, you know, assignments and tests, because they are easier for students to solve. Here's why. In an inelastic collision, the only thing that's true is that momentum is conserved. And I can't stress this enough. Conservation of momentum is conservation of momentum. Okay, it doesn't matter whether there's friction or no friction. It doesn't matter if there's deforming or no deforming. Conservation of momentum is conservation of momentum. So even in an inelastic collision, conservation of momentum is true. And I showed you the very first opening to this two-dimensional momentum lecture. We set up a situation where two objects strike each other, and there was 7 variables and only 2 equations, which means I have to give you 5 of the 7 variables. This means it's fairly easy. All you have to do is one substitution, right? Eliminate one of the variables, solve for the one of the 2, and then plug it back in and solve for the other one. That's fairly easy to do from a student perspective. So from an inelastic collision standpoint, you'd really be hoping to see some inelastic questions on either the assignment or the quiz, or when you're doing problems, because it is honestly easier for students to do. Now, contrasting an inelastic collision is something called an elastic collision. And an elastic collision is literally the exact opposite. And that is when you deform something, but then when you let go, the object springs back and retains its original shape as an elastic band would. So a spring is obviously an example. A rubber band is obviously an example. But technically, every object everywhere, you know, has the ability to strike or hit or collide with another object, and you know, will obviously deform in some way during the collision. And that collision is deemed elastic or inelastic based on whether or not something cracks or breaks or deforms. Technically speaking, when you're walking, there's a collision between your foot and the floor. And we know from previous physics, when, you know, a car, you know, collides with something, when we did energy, we studied the stopping distance, the distance at which the car moves forwards after the collision in order to come to stop. So every time there's a collision, it's not like an instantaneous stopping of these objects. So when you're walking on the floor, there is a collision between your feet and the floor, and just because it's not a car colliding with a pole or something like that, it's still a collision. The physics still applies. So there actually has to be a stopping distance over which your foot comes to rest. And believe it or not, you know, part of your foot kind of squishes, and part of the floor will actually deform as it's cushioning the blow from the collision of when you're walking. And this is why you know, really hardwood floors sometimes hurt people's knees when they walk on them all day. Or if you've ever worked retail, or you're a waitress or something like that, or you know, you work, well, I said retail, when you're walking around and the floor in your workplace is really hard, and let's say you don't have, maybe you wear like Converse or something. Converse are known to be kind of really like a basic shoe. The sole of the Converse is just kind of hard rubber. So if you're walking around on like a shoe that isn't designed very well, then when you walk, the force of the impact from the collision is going to go right up your leg and hit your knee joint, and then the cartilage in your knee is going to take the brunt of the force. Whereas hopefully if your bosses and managers are better to their employees, people who do a lot of standing, like at cashiers or something like that, they have a little mat to stand on. And the whole point of a mat is to provide a softer surface, so when you walk on it, it provides more of a cushion, and that elongates the distance of the collision, which reduces the force on your joints. So the notion of an elastic collision then would be, when you're stepping on a mat and you step off of the mat kind of returns to its position. So like that would be most mats, I guess, would be like if it's a rubber mat, I would say it would be like an elastic collision. If it's like a foam mat, when you drop a ball in some foam, it just kind of sinks in the foam. That would be an elastic collision. Another example, which is on the slide right now, are things like sports balls, basketballs, baseballs, tennis balls. They're bouncy, and the reason why they're bouncy is because when they collide with the ground, the ball will deform, and then when the collision is done happening, the ball will re-expand and then launch itself back upwards. That's like what dribbling a basketball does. In the event that you have an elastic collision, not only is momentum conserved, because momentum is always conserved in a closed system, not only is momentum conserved, but specifically kinetic energy is conserved. Specifically, kinetic energy. Not all energy. You can still lose energy due to sound and this and that and the other thing, but specifically the kinetic energy is conserved. So a common mistake here, is that students try to use E total equals E total prime. That's wrong, all right? It's the kinetic energy, and specifically the kinetic energy is conserved. Now, let's look at this for a second. Momentum gave us two equations, okay? It gave us the X and then the Y. And there were 5 variables. Sorry, there were 7 variables and 2 equations, which means I had to give you 5 variables and you had to solve for 2 of them. Now, with an elastic collision, we have a 3rd equation that we can use. Now, a 3rd equation doesn't necessarily make something harder. Sometimes it makes it easier, but it kind of depends what variables are introduced in the 3rd equation. So if you look at the total, at the kinetic energy is 1/2 mv squared. So the variables involved in this 3rd equation are exactly the same variables as in the 2 previous equations. So even though we're adding a 3rd equation, we're not necessarily adding any new variables. We're adding, all the variables in this new one are the same, it's a subset of the variables in the other 2. So in this case, let me just change my color here for a second. In this case, there are still 7, oop, that's a terrible 7. In this case, there are still 7 variables, but only, but 3 equations. So this means we only have to give you 4 variables. That's terrible variables. So now you have to solve for 1 extra variable compared to before. And this is what I was saying before, with an inelastic collision, they're actually easier for students to solve because we have to give you more information and you have to solve for less information. So inelastic collisions, I think, are easier for students to solve. Elastic ones, I think, are more fun, they're more interesting, but they're definitely more involved mathematically to solve. So here's kind of what this looks like here. If you have an elastic collision, these are the same. Oh, you can't see that because that color does not go well on black. These are the same as before that we got from above in that chart. However, here is your third new equation, right? This is just conservation of kinetic energy. So this situation here, we have this one is moving and this one is stationary. So the total kinetic energy before the collision just is a result of object one. And then after the collision, we have two objects that are moving. So this is the kinetic energy after the collision. So 1/2 mv1 squared is just before, and then 1/2 mv1 prime squared is the kinetic energy of object one after, and then you've got the kinetic energy of object two after. So that's what it would look like. Those are what your three equations would look like in the event you have a two-dimensional elastic collision. Now you might be thinking to yourself, but Mark, you know, all the two-dimensional examples you've done, there was always one mass that was stationary. You're right. If you are trying to question that, most of you probably aren't, but if you are, you're questioning that, it's okay. I will get to that at the end of the lecture. I'm going to make you a promise that you can always force one of the two objects to be at rest before your analysis. There's a trick that you can do. And we've actually seen the trick before earlier in this course, but I will remind you kind of later on. But for now, we're going to look at all the two-dimensional cases. We're going to look at one object is moving and one object is stationary, because you can always sort of force that to be the case mathematically. Okay, I think enough of the theory. I think we can just kind of jump to a problem now to kind of show you how to solve something and kind of how momentum can be used in conjunction with energy. So here we have something called a ballistic pendulum. And in the olden days, something as crude as this was used by a lot of forensic technicians at crime scenes. You know, you can study a lot of forensics from a crime scene this way. Now, of course, there's more sophisticated methods in modern time, but this is a really good illustration of kind of the fundamental physical principles of, you know, forensic science, for instance. So here's the example. A ballistic pendulum was used to measure the speeds of bullets before the invention of electronic timing devices. The version shown in figure 4, which is from the typed notes, so I guess what we're looking at below is figure 4, consists of a large block of wood of mass capital M. Oh, I'm still writing in red, so let's change this to black. M equals 5.4 kilograms, hanging from two cords, fine. A bullet of mass little m, oh, that's going to be a problem. M, oh, that's a terrible little m. Okay, hopefully that's different enough. 9.5 grams is fired into a block of wood and quickly comes to rest, all right? So the bullet is embedded in the block. The block plus the bullet then swings upwards, and the center of mass rises a vertical distance of 6.3 centimeters before the pendulum comes momentarily to rest at the end of its arc. Okay, fine. What is the speed of the bullet just prior to the collision? Just prior to the collision, which means initial speed. What is okay, cool. So there's the question. We're given both masses. We're given the vertical height of this block bullet combination after the collision, and we're wanting to know what the muzzle velocity is of the bullet. So trying to wrap your head around what's going on here, I would, if this is new to you, I would stick to basics. I would just kind of set up an equation that involves the quantity they're asking about. So they're asking about the initial velocity. So I would make note of the fact that there's a collision that happens between the bullet and the block of wood. So I would say if there's a collision, we should probably start with momentum total equals momentum total prime. So that's what I was talking about, developing the sort of intuition. Yes, I know we're in the momentum unit at the moment, so it should be kind of obvious we start with momentum, but on a test, you know, there's going to be energy, momentum, and torque. So you kind of have to kind of figure out what to do there. So anyway, collision means momentum. Beforehand, we only have the momentum of the bullet because the block was stationary and at rest. And then afterwards, we have the bullet and the block amalgamated together, which means we have the bullet plus the block kind of acting together as one mass. So we have to figure out, is this elastic or inelastic, right? A collision took place, and we have to figure out, is it elastic or inelastic? So the definition of elastic was if you deform an object, it will eventually spring back and retain its original shape. An inelastic collision is when you deform an object, it does not spring back and retain its shape. So here, I would say it's inelastic, also because the slide says so. It says inelastic example. But in case I didn't tell you that, if a bullet gets lodged into a piece of wood, inherently those objects are different than when they started. You know, they're one mass lumped together. So the mass is changed after the collision compared to before the collision. So this is what makes it inelastic. And if it's inelastic, we don't know anything about the kinetic energies. Obviously, it's not like all the kinetic energy was burnt up, right? Because there's some kinetic energy left, right? The whole system is moving forward, but we can, by no means can we say that the kinetic energy is conserved here. So let's kind of introduce the variable they're speaking about. So let's see here, momentum of the bullet is going to be little m v initial, and the momentum after the collision is going to be little m plus capital M times v prime. Okay, what do we have? What do we need? Well, we have little m, we have capital M. Do we have v prime? I mean, obviously we're asked for this, but we don't have v prime either. So then I'm like, crap, you know, I thought I was onto something, you know, I'm trying something new. I'm trying to sharpen my critical thinking skills and trying to practice physics like Mark's asking me to, but I've hit a dead end. What do I do? Well, you see here, the quantity v prime is what we need. Is there something else we know from the statement of the problem that can help us obtain v prime? So I'm looking here, I've used mass, I've used both masses, but what I haven't used is I haven't used the change in height. So I think to myself, is that in any way related to the v prime that I need? The answer is yes, you use conservation of energy. You think, here's your intuition coming into play. You know they're related because if v prime was larger, meaning the speed of this block bullet combination, if it was large after the collision, then it would actually travel up the swing farther. If the speed of the mass bullet combination was small, then it actually wouldn't really go that far up after the collision. So you know the two quantities have to be related. There's your problem solving skills kind of kicking in. Next, you have to kind of figure out exactly what that connection is. How is the speed of an object at the bottom of a trajectory related to the height at which that object is able to obtain? And that answer is conservation of energy. So we now have to take a break from the momentum, and we can say E total equals E total prime. And I know you're probably thinking, but Mark, it's inelastic. You said kinetic energy wasn't conserved, let alone conservation of energy. You know, you said a common mistake students make is they try to use conservation of energy here. You have to understand, though, this analysis is after the collision already took place. This is the analysis of the collision, and this is the analysis after. Can you mute yourself, please? After the collision. So after the collision, it is fair game. After the collision, conservation of energy absolutely applies. After the collision, this bullet mass combination is going to have some sort of total energy, and then something happens, the whole mass bullet system swings upwards, and then that kinetic energy gets converted into gravitational potential energy. So after the collision, you can absolutely use conservation of energy, but during the collision, at best, you could only use conservation of kinetic energy, and you can only do that when you have an elastic collision, which we do not in this case. Okay, going through it, I'm going to have 1/2 mass total v prime squared, where v prime is the speed of this mass bullet combination after the collision. And that kinetic energy is going to go into gravitational potential energy. So here we are, we've actually obtained a formula for the final velocity as a function of height reached. So you see the masses cancel, and when I rearrange, I'm going to get the square root of 2g delta h. So that's what I'm going to do. I'm going to go here and say mvi equals mass total times v prime. Well, v prime is going to be the square root of 2g delta h. And this means that your initial velocity of the bullet before the collision, meaning the muzzle velocity, is going to equal mass total over the mass of the bullet times the square root of 2g delta h. And there you go. So that's kind of how old school forensics kind of happened. All right. Let's move on to an elastic example. Making this smaller. Okay, so with an elastic example, we have to ask ourselves, again, I'm telling you it's elastic, so ahead of time you're going into the question knowing it's elastic. But if you had to figure this out for yourself, you're asking yourself, okay, the collision happens, do the objects stick together, yes or no? And is there any, deformation of any of these objects? So here, if we read the question, we have two different pendulums. We have a smaller mass on a rope and a larger mass on a rope. And the large mass is left at rest at the bottom, and the smaller mass is lifted up and primed, and then the smaller mass is let go. And the smaller mass swings down and strikes the larger mass that is at rest at the bottom of the pendulum. And then afterwards, the mass 2, the larger mass, kind of swings up independently of mass 1. So this tells me that during the collision, these metal balls probably deformed a little bit and they were no longer perfectly circular during the collision. But after the collision, they bounced back. They're both, spherical balls. They weren't flattened into a pancake, and they did not stick together. They rebounded apart from one another. So this is a telltale sign of an elastic collision. So not only do we have conservation of momentum, we also have conservation of kinetic energy. So let's read the question in more detail. Two metal spheres are suspended by vertical cords, initially just touch fine as shown in figure 5. Sphere 1 with a mass of m1 of 30 grams is pulled to the left at an initial height of 8 centimeters, and then it's released from rest. Okay. After swinging down, we know M2 is 75 grams. What is the velocity of V1 prime just after the collision? V1 prime equals question mark. Okay, is that all we're given? After swinging down, it undergoes an elastic collision with sphere 2, whose mass is bliss. What is, okay, there we go. So we don't actually care about mass 2. I suppose we could solve for it if we wanted to, but the question doesn't specifically ask us to solve for V2 prime, for instance. We could actually do you one further. We could actually calculate how far up the velocity goes. Sorry, how far up the mass 2 goes after the collision. If we wanted to, we don't have to, but if you wanted to, you can. Okay, so again, new problem, trying to kind of figure out where to start. Perhaps we know there's a collision, so maybe we just start with writing down conservation of momentum. So P total equals P total prime. And the momentum before the collision is going to be M1 V1. And then the momentum after the collision is going to be M1 V1 prime plus M2 V2 prime. Okay, so what do I have? What do I need? M1 we have. Let me just change my color here. M1 we have, M2 we have. That's it. We don't have V1, we don't have V1 prime, and we do not have V2 prime. Now, the question is specifically asking for V1 prime, which means we have to sort of swap out all the other variables. We have to swap out V1, we have to swap out V2 prime. So now I have to figure out how to do that. V1 prime, okay, V1 prime is going to be the velocity at which the mass 1 strikes mass 2. Is that in any way related to the information stated in the problem? Well, I've already used these. That means this is probably the key. Is the velocity at which object 1 strikes object 2 related to the height at which object 1 was elevated? Obviously, the answer is yes. We know this from well, for one, intuition, quite frankly. The higher something falls from, the faster it's going to end up going at the bottom. So there's your intuition coming into play, but also your experience with conservation of energy. In fact, we just did that in the previous problem. So we actually know this can be solved for with root 2 GH. We literally just solved for that in the previous question. So yes, I'm skipping a few steps here, but only because we literally just did that in the previous problem. So we know that this now is M1 times root 2GH equals M1 V1 prime plus M2 V2 prime. So we're a little bit better. Now, if you look, we have M1, we have H, we have M1, we have M2. So now this is what we're asked for, but we still don't know anything about V2 prime. So now we ask ourselves, okay, well, I tried to go, the usual method. I tried to, when I got stuck, I went to go look at what was in the question and try to use some other information in the question. I've done that. I've used everything in the question, and that only solved half of my problem. So there must be another piece of the puzzle that I'm missing. And in fact, the piece of the puzzle is that it's an elastic collision. So this is where I was saying with an elastic collision, you have 3 equations for a 2-dimensional collision. For a 1-dimensional collision, you'll only have 2 equations. But we're allowed to ask for an additional variable to be solved. So that's why I'm saying it's a little bit more difficult for students when they're solving an elastic problem. This means E kinetic equals E kinetic prime. So the total amount of kinetic energy beforehand was simply the kinetic energy of object 1. Oops. And then after the collision, we have the kinetic energy, we have the kinetic energy of the first ball plus the kinetic energy of the second ball. So that's what the conservation of kinetic energy says for an elastic collision. And again, we can actually use this quantity in here. So that makes things a little bit easier for us. 1/2 M1 2GH equals 1/2 M1 V1 prime squared plus 1/2 m2 v2 prime squared. And of course, I am running out of space. All right. I know ahead of time I'm going to need more space. So I'm going to insert some more space. All right, and now we just kind of go with the flow. Mass 1, mass 1. Oh, we actually can't. We can't even, we cannot, there we go. We can't even cancel those. Okay, so we want to eliminate v2 prime. So v2 prime equals, this is going to be, oh, we can cancel the halves. So v2 prime, well, let's do this in steps. It's going to be m1. For now, I'm going to leave this as v1 squared, just for now. It's fewer variables to write, and I'm lazy. So I'm going to keep it as v1 squared throughout, and then right at the end, I can switch it. Just because I'm lazy, I don't want to write out 3 symbols when I can write 1. Minus m1 v1 prime squared. I'll put the word lazy here, just because I don't want to write out the symbols. Okay, and then this makes, oh, there should be a squared there. And v2 prime squared is going to be m1 v1 squared minus m1 v1 prime squared all over m2. And v2 prime is going to equal the square root of m1 v1 squared minus m1 v1 prime squared all over m2. Oh boy. Okay, so that was a lot of work just for v2 prime. Now that we have v2 prime, we can go back to this equation. We have m1 square root of 2gh equals m1 v1 prime plus m2 v2 prime. And we can go back and add this equation here. m1, oh, v1 squared, right, is going to be 2gh minus m1 v1 prime squared all over m2. Oh boy. All right. And now I think the only unknown is v1 prime squared. Let's figure that out. Just verify that, shall we? M1 we have, H we have, M1 we have, this we do not have. M2 we have, M2 we have, M1 we have, H we have, M1 we have, and this we don't have. One equation, one unknown. One equation, one unknown. So we are able to get to an answer. You will realize that this ends up being a quadratic equation. This ends up being a quadratic equation. Okay, so when you're solving the quadratic equation, it's going to get pretty messy. It's not fun. So you can do it. You can sit through and you can try to do it. I'll tell you now that the answer ends up being, I'll just fast forward to the answer. V1 prime ends up being M1 minus M2 over M1 plus M2 times the initial speed of the object 1. And in our case, the initial speed ended up being root 2gh. In our case. In a different case, it may not be, but in our case, V1 initial was root 2gh. So if you follow through all of the algebra and the quadratic equation and all that stuff, you will eventually end up getting V1 prime to be this. Now, I will say that this whole process maybe a different color here for you. This whole process of rearranging is in the typed notes on page, let me just check for you, on page 18 of the momentum typed notes. So I just going through solving a quadratic equation in lecture, I don't think it's a good use of lecture time, especially since I've provided with you the derivation, the full derivation on the typed notes as well. So if you care about the act of rearranging and the act of solving, you can go look at page 18. But that's the setup for you. I hope you can now appreciate when I say that an elastic problem is significantly harder for students to solve than an inelastic problem. Look, we did an inelastic problem just before this, and I was able to come up with the final derived equation fairly easily without a lot of effort. And with an elastic problem, there is a lot of effort, and there's so much effort, in fact, that it would not even be a good use of time to show you the rearrangements and all the algebra in lecture. That's how much harder an elastic problem is mathematically to solve. So with that said, it is really good to develop some intuition with an elastic collision. Inelastic collisions, yeah, it's good for some intuition too, but inelastic collisions are mathematically quite simple to solve for. So you almost don't need there isn't as much of a need to develop intuition with inelastic collisions. But with elastic collisions, the math is just ridiculous. So it's really good if you can help kind of simplify the math by understanding and picturing in your head what's going on. And then that way you can make some shortcuts and make your lives easier. So first of all, I will say most textbooks will show you these formulas. Is this red? No, this is blue. These are derived formulas. They're not base equations, okay? Conservation of momentum is a base equation. These are derived formulas. A derived formula will always have a set of assumptions. So these are the derived formulas for the speed of object 1 after a collision and the speed of object 2 after a collision. Now, here are the assumptions that go into these two equations. 1, the collision was elastic. So if it's an inelastic collision, do not be using these equations. And the second assumption is that one object was initially at rest. I cannot stress this enough. The very first two-dimensional problem we did with the billiard ball, and I constructed that chart, I told you we had to assume, well, we didn't have to, I assumed that one of the two billiard balls was at rest. And then later in the lecture, I told you, you might be wondering, hey, Mark, why are we only doing questions where one object is at rest? And I told you, I promise you can always force one object to be at rest in a two-object collision. And in real life, this may not make much sense, because in real life, you can easily have two objects that are moving with a non-zero velocity and then collide. So you might be thinking, hey, Mark, well, that's just a bold-faced lie. Like, obviously you can have two objects that are moving that collide. There is a mathematical trick that you can make to force one object to always be at rest before the collision. And we will talk about it at the end of the lecture. So that's where these, that's why textbooks really go through the headache of deriving these equations, because when you have a two-object collision, you can always force one object to be at rest. But we will discuss that later, as I said. Anyway, here's the intuition. The math is hard for an elastic collision. Here's the intuition. Let's look at these equations. V1 prime. the velocity at which object 1 moves with after a collision. Okay. You'll see here that in the top, there's a subtraction of m1 and m2. So if m1 is larger than m2, then this subtraction of m1 minus m2 will be positive, right? Because m1 is larger than m2. Now, of course, if it's much, much bigger than m2, then the subtraction will be very positive, but that doesn't matter. If m1 is just bigger than m2, then you know the sign, the plus minus, the sign of v1 prime is going to be positive. Or more specifically, it's going to be in the same direction as v1. Now, what does this mean? It's one thing to sort of see this mathematically. It's another to develop intuition of the math. So what does that mean mathematically? If v1 prime has the same sign as v1, that means the direction of the velocity before the collision is the same as the direction of velocity after the collision. That means, an example of this is when a heavy truck hits a light car. And you can picture kind of what happens in real life. If you have a heavy object striking a light object, then the heavy object will actually follow and continue through the collision. It will not bounce back. It'll follow through the collision. And you can definitely picture this in real life. If you don't believe me, try this with like objects in your house. Now, the reverse is true. If mass 1 is less than mass 2, then that subtraction is going to be negative. And that means that the direction of the velocity of object 1 after the collision is going to be opposite to its initial velocity. And this means it'll ricochet backwards, and it'll go back to where it came from. It'll kind of trace its steps backwards. So the reverse example is if a car hits a truck. I don't know if you want to picture that. If you want to picture something else, picture a tennis ball hitting a wall. If you throw a tennis ball at a wall, the tennis ball bounces back. Because what's heavier? A wall is obviously much heavier than a tennis ball. So, when you have a light object striking a heavy object, the light object will literally just bounce backwards. That's what that means. And we'll look at extreme cases in a second. Obviously, another fun one is when the two masses are equal to each other. And this happens when you have identical masses. Now, in real life, it's very rare and uncommon for two masses to be identical. Like, even no two cars are the same, right? For instance. But a common occurrence of when this would happen is, say, when you play pool. You've got all the pool balls are all the same radius, or all the same weight. They're different colors, but who cares? The colors, just because a ball is yellow or red doesn't mean it's heavier than the other one. So in pool, all the balls are the same. And when mass 1 equals mass 2, look at the math. When mass 1 equals mass 2, that subtraction is going to be 0, which means mass 1 is going to come to rest and then transfer all of its momentum to mass 2. And then mass 2 is going to continue on with the initial speed of v1. Okay, now, there's two cases I have not talked about yet, and that's because I want to insert some room, because we need some room to sort of explore the math here. So one case is when mass 1 is not just bigger than mass 2, but when mass 1 is very, very, very much bigger than mass 2. You can tell how good my English is with my bad grammar. Let's look at the math. If mass 2 is very small in comparison, then v1 prime, which we know is m1 minus m2 over m1 plus m2. Oop, what's going on there? Oh, it's still, okay, sorry. v1 prime equals mass 1 minus mass 2 over mass 1 plus mass 2 times the initial speed. If mass 2 is peanuts, let's say a transport truck hits a ping pong ball, You know, a transport truck weighs, you know, tens of thousands of kilograms, and a ping pong ball weighs like 10 grams. So if you have 10,000 kilograms minus 10 grams, a calculator is not going to know that difference. This is approximately equal to mass 1 minus 0 over mass 1 plus 0 V initial, which is mass 1 over mass 1 V initial, which is just V initial. So that's why this says when mass 1 is really, really large, then V1 prime continues on mostly unaffected. And you can picture this intuitively. We're building intuition here. Intuitively, if a transport truck is driving along and someone just throws a ping pong ball in front of the transport truck because they're being a hooligan, the ping pong ball is just going to bounce off the transport truck, and the transport truck's not going to have any knowledge. Like, it's going to be almost completely unaffected, right? So all of these physics equations and math equations that we're developing, they have to represent real life. That's the whole point of physics, is we're trying to explain the world around us. So whenever you're in doubt, think about what would happen in real life. Whatever equation you derive has to be representative of real life. Now, what does that do to V2 prime, meaning the small object? Yes, if you throw a ping pong ball in front of a moving transport truck, the transport truck's going to have no idea that there was even a collision. But the ping pong ball is going to know, because it was just hit by a very massive object. So if we look at the math here, the math says the V2 prime, the speed at which the small object ricochets off with, is going to be 2m1 over m1 plus m2 v1. Well, if mass 2 is really small in comparison, then what we end up getting is 2 times m1 over m1 plus 0. We can, or I should really say approximately equals 2 here, v1. And this is going to be 2 m1 over m1, so those cancel, and that gives you 2 v1. And this is actually very counterintuitive. You can anticipate that, of course, the small ping pong ball would be affected by the collision. Like, that's not hard to get on board with. And, you know, if a big transport truck hits a small ping pong ball, you can understand that the ping pong ball is going to fly forward. Like, that's not the question here. The question here is, specifically, it'll fly forward at 2 times the speed of the transport truck. It's that value of 2 that seems very counterintuitive. What's more counterintuitive, that it doesn't seem to really be a function of how big that difference is. As long as mass 1 is sufficiently larger than mass 2, you know, it could be 1,000 times larger, it could be 100 times larger, it could be 10 times larger. It doesn't matter. As long as it's sufficiently larger, it only ricochets off with 2 times the speed, which is kind of really interesting. That part is counterintuitive. So that's why we do need these equations. We can't just throw out the equations and just do physics without equations. It's important to develop intuition behind these equations, but you know, the equations still do provide some insight into what's happening. So that's kind of interesting. And the other one is, the other extreme is not as interesting, I would say. It's the other extreme is quite intuitive. The other extreme being, let me just change my color here. The other extreme is when mass 1 is really, really small compared to mass 2. And that would be like a tennis ball hitting a brick wall, for instance, or a tennis ball hitting a car or something like that. So if you look at the equations here, v1 prime, m1 plus m2, nope, sorry, minus m2 over m1 plus m2 v1. If mass 1 is very small, you can sort of approximate mass 1 to be 0, and then you get minus m2 over m2 times v1, which means you're going to get minus v1. So this tells you that if you have a really light object striking a very heavy object, then the light object simply bounces off, and returns backwards with the same velocity that it hit the object with. And moreover, if you look at V2 prime, if you look at V2 prime, V2 prime is 2m1 over m1 plus m2 v1. Again, if you approximate mass mass 1 to be small in comparison, then you're going to get kind of 0 over m2 v1, which equals 0, which is what this is saying here. It means if you have a really light object that strikes a very heavy object, that heavy object isn't really going to move after the collision. If you throw a tennis ball at a car, even if it was a block of ice and it was frictionless, if you throw a tennis ball on a car, that car isn't really going to move anywhere. I mean, technically, it'll move a little bit, technically. But, you know, this is the intuition. The intuition tells you that that car isn't really going to move much, if at all. In real life, when there is friction, it's certainly not going to move. Okay, normally when I teach this class, I like to do a bit of a demonstration here with dynamics charts. I do a demonstration for you guys. I illustrate kind of that chart. What I do is I put a lot of mass. I put a lot of mass on one cart to make mass 1 much, much bigger than mass 2. And I like to show you in real life, if we were in a classroom setting, I like to show you in real life that the mass 1 is mostly unaffected by the collision, and mass 2 kind of rockets off really fast. And I tried to find a YouTube video of this, but there doesn't seem to exist one. So maybe sometime this weekend, if I find some time, you know, I might pop into the campus and get the equipment out, and I might try to film it for you guys and post it on YouTube so you can kind of see it. You know, we'll see. I don't even know if I'm allowed in there. I was about a month ago. I don't know if things have gotten worse or better. I've got no idea. So I'll see. I'll see if I can get into campus and see if I can film this for you. The other demo that I like to do in person so you can see it in real life is the basketball and the baseball example. Here, when they're moving together, the basketball is much, much, much larger than the light baseball. And when they collide, when they hit the ground, when they collide, you know, they collide with the same speed, but after they bounce off of each other, and there's a collision that happens between the basketball and the baseball, and this mass 1 is very, very big compared to mass 2, so this kind of rockets off with twice the initial speed. And this is mostly unaffected, so this just goes up at V1. So this demo was an example of mass 1. Oh, you can't really see that on black. This example was an example where mass 1 was much, much, much larger than mass 2. And it's fun to see in real life because you actually, you know, I drop these things from waist height, and the tennis ball rockets off and it almost hits the ceiling of the amphitheater. Like, that's how high it goes. So it's fun to see in kind of real life. Unfortunately, I can't do this in real life, and this is really hard to film because, you know, the tennis ball rockets off so fast that, you know, it would be really hard to move the camera to see both the tennis ball and the basketball at the same time. However, I was lucky enough to find some sort of video with this on YouTube. It's not great, but it's something. So we're going to take a little bit of a break, and I'm going to show you that demo on YouTube. And hopefully, you know, seeing what happens in real life in this video makes a little bit more sense now that you've seen the physics behind it. So let's do that now.
Hi, Dave Maiulo here, Rutgers Department of Physics and Astronomy. We're doing some outside fun summer demonstrations right here, and you really don't want to be using any kind of projectile motion inside, so we're going to show you this and how it works outside. Here's a tennis ball, a small ball that bounces very well. And here is a basketball, a much larger ball that also bounces well. Let's look at some momentum conservation. That small ball is going to be hit by the large ball, and it's going to transfer the momentum of the large ball to the small ball. When that happens, we're going to see that this ball is going to jump really high, and you can replicate this as many times as you want when you're outside. And you can see, yeah, we launched our tennis ball. It works really well by getting hit by that large ball. The large ball stays here as it transfers its momentum, kicks that ball way out. We launched our tennis ball. It works.
All right. So that was the best video I could find on that demo. Trust me when I say it is definitely much more glorious when you can see it in real life. You know, sometimes I can try to aim it, and I can try to hit a light bulb or something, but it is definitely, it's more prolific in real life. So I wish I could show you that, but maybe sometime this week or in the weekend I can go in if I'm allowed to, and I can try to film the carts example, because that does really provide insight, physical insight, a real life example into the chart that I showed you. By the way, that chart is available in the typed lecture notes, as well as those two equations. The derivation of the equations was on page 18. The final product of those equations are on page 19, as well as that chart. So I strongly recommend you go and you do that. Okay, we are nearing the end of momentum. I've told you now a few times that you can always force, when you've got two objects colliding, you can always force one of the two objects to be zero, not moving initially is what I should say. And we developed a whole system of analysis with that. We did the chart method in 2 dimensions. We did elastic collisions, and we did a bunch of derivation math that I had to sidestep for time purposes, and I had to direct you to the typed lecture notes. So we put a lot of work into developing equations with the assumption, specifically with the assumption that V2 initial was equal to 0. So it'd be better, I'd better be able to follow through on my promise that you can always force one of the objects to not be moving before the collision. So let me show you how to do that now before I let you go. That we've actually seen this trick in the very first lecture, where we had, what was it? I think it was the high-speed locomotive and the freight train that were on a head-on collision. And the freight train was traveling forward very slowly, and the high-speed locomotive was traveling forward very quickly, and it had to come to rest. And there were 2 ways to solve the problem. One way was the hard way, where you keep all of the velocities with respect to the ground. But there was an easy way where you set, you change your frame of reference away from the ground. You change your frame of reference with respect to the slow moving object. So that's the trick. The trick is doing a change of a frame of reference, which is a bit of a mouthful, a change of a frame of reference. Maybe actors should start saying that before they go on. I don't know what they usually say. There's a famous saying that they usually say, but a change of a frame of reference kind of seems equivalent to practice with. Anyway, I don't know. I'm not an actor. What do I know? So let's see how this is done. In figure 6, block A, which is known to have a mass of 1.6 kilograms, slides into block B, which is heavier, along a frictionless surface. The directions of the velocities before the collision are indicated in the picture, presumably. The corresponding speeds are the velocity of block A initially is 5.5, the velocity of block B initially is 2.5. What is the speed and the direction of the resulting velocities? So, students might be tempted to say, okay, it's an elastic collision. Let's just use those equations that Mark just gave us above. Although I agree that eventually we will need to use those equations in order, and this is why I have a problem with students just wanting to memorize equations. These derived equations have a set of assumptions that went with them. The assumptions were, if you remember, let me scroll up. The assumptions were 1, that the collision is elastic, check. 2, that one of the 2 objects was initially at rest, not check. Here in this question, both objects were moving, which means those equations are not valid. And this is where a lot of students get into deep problems when they try to do physics tests. Their approach to learning and their approach to physics is to just memorize. And that often leads to very, very poor performance. And it's simply because you cannot memorize physics. You have to understand it. You have to live it. You have to breathe it. You have to see it. You have to understand it. It's honestly one of the only science disciplines that you really truly have to live and breathe in order to fully appreciate and understand the physics concepts. And luckily, though, for you, although it's the only one that requires you to understand it, it gives you a great opportunity to do so, because you can actually experience it. Most of what we're talking about is things that you can replicate in your day-to-day lives. If you don't believe me when I make a claim, just try it. You know, take a tennis ball and a basketball and try it. Go home, you know, after the lecture's done, take a big ball and take a small ball and drop them one on top of each other, and you see for yourself what happens. So although physics does have a high threshold of brain power that is required of students, it provides itself very well for students to actually think and practice it. Unlike some of the other disciplines like chemistry and biology, which are abstract and subatomic, and it's really hard to think of intuitively. So I can understand your need of wanting to come in to memorize, but please try to kick yourself of that habit in this class. Okay, anyway, back to this. Let's force the frame of reference of object 2. Well, let's force our frame of reference away from the ground to the frame of reference of object 2. So I will say, oh, I'm writing in red right now. Let's say the velocity of object A with respect to the ground was given to be 5.5 meters per second. And we want the velocity of object A compared to object B. Well, if you remember from our first lecture, we said in order to do this, it's going to be the velocity of object A compared to the ground, plus the velocity of the ground compared to object B. Okay, so that was our frames of reference equation. We have to assign a direction because we have a bit of a coordinate system going on. So let's say right is positive. Okay. What do I have? Well, I have VAG. VAG is 5.5. Do I have the velocity of the ground compared to object B? No. What I do have is I have the velocity of object B compared to the ground. That's going to be 2.5. So with vectors, if you need the opposite, you just add a negative sign and swap the indices. So this is going to be the velocity of object A compared to the ground minus the velocity of object B compared to the ground. Okay, so now that I have my equation, I have to drop my vector signs according to my coordinate system. So VAB is going to be given by, now VAG. VAG is traveling to the right. The velocity of block A compared to the ground is traveling to the right, and right was deemed positive. So this is going to be positive VA initial minus, and VBG. VBG, the velocity of object B compared to the ground, is also traveling to the right. So this is also going to be positive. So the velocity of block A compared to block B is going to be VA minus positive, so just minus, VB. And this makes sense. If someone is traveling forward at 2.5 meters per second, and you're behind them and catching up to them, and you're traveling slightly faster, it's going to look like you're approaching them at 3 meters per second, which is really what this is, 3 meters per second, right? You experience this all the time when we're driving on the road with fellow cars. Okay, so there's my frame of reference. Also, we want to know the speed of object B compared to object B. I'll give you a hint. The answer is 0, obviously. What's the speed of me with respect to me? 0. But if you want to do it mathematically, it would be the speed of object B with respect to the ground minus the speed of the ground with respect to object B. Oh, sorry, plus. And this is going to be V of object B with respect to the ground minus V of object B with respect to the ground, right? We flip those indices and add a negative, and then that simply equals 0. So the speed of object B with respect to itself is always 0. And this is what I'm saying, maybe I'll write this in red. This is what I was saying by C. I can always force one object to appear to have an initial speed of 0. That's how you do it. Taking this information, we now say VAB equals 3, VBB equals 0. Now we can use our derived equations. So now, what are they asking for? What is the speed in the direction of the resulting velocities? So now I can simply say V1 prime equals M1 minus M2 over M1 plus M2 V1. And that's going to be, what's mass 1? 1.6 minus 2.4, 1.6 minus 2.4 over the sum, and the sum is going to be what, 4? 4. And V1 was 3. So please make note that this 3 came from the adjusted velocity. Wait, why did that turn black? That's weird. Ooh, there we go. Okay. And if you go through this, I think you're going to end up getting minus, oh, I'm still writing in red. You're going to end up getting minus 0.6 meters per second. So the minus sign means it travels backwards. Does that make sense with our intuition? Yes, because mass 1 is less than mass 2. So according to the chart, it's going to ricochet backwards. And V2 prime is going to be 2 times mass 1 over mass 1 plus mass 2, V1. So this is going to be 2 times, what was mass 1? 5? Nope, no it wasn't, 1.6. Mass 2 plus mass 1 is going to be 4. V1 is 3. So if you plug all those numbers in, you're going to get 2.4 meters per second. Okay, so we've solved for our final velocities. I know it's 1 o'clock. Give me just a second. I'm almost there. I just have to add a bit more space. Okay, these velocities are in a different frame of reference. So let me just put that here. Note, these answers are in a shifted frame of reference. This means we actually have to take these numbers and transform them back to our original frame of reference and then report our final answer. So we go backwards and we say the velocity of object A with respect to the ground after the collision is going to be the velocity of object A after the collision with respect to object B plus the velocity of object B with respect to the ground, right? These two things in the middle will match. So this is going to be minus 0.6 plus, what was the speed of object B? 2.5. 2.5. So our answer is actually, at the end of the day, going to be 1.9 meters per second. So this is where things get a little bit conceptually confusing, right? Our intuition of whether or not something's going to bounce back or travel through the collision was assuming one of the two objects was stationary. This, in real life, this scenario, both objects are moving. So we can put ourselves as a passenger seat, in a passenger seat of object 2, and turn around and look backwards. And if I turn around and look backwards and I see object 1 collide with me, to me, sitting in the passenger seat of object 2, it'll look like object 1 after it collides with me, it'll look like object 1 is traveling backwards, meaning the distance between myself and object 1 will increase. However, for a spectator viewing on the ground, the spectator will see that after the collision, both cars actually move forward. But the distance between the two objects will increase, but both objects will move forward. Similarly, I can do the same over here. Velocity of object B compared to the ground is simply going to be, when I'm getting edge effects, the velocity of object B compared to the ground prime meaning after, is going to be VB compared to B prime plus VB compared to the ground. So again, the inside ones match. So that's what we want. And this is going to be 2.4 plus, what was it? Oh, it was 2.5. 2.5. So this answer is going to be what? 4.9 meters per second. So there you go. So you'd say, therefore, the speed of block A after the collision will be 1.9 meters per second, and the speed of block B will be 4.9 meters per second. So it's important to have this therefore statement because you as the physicist or the scientist, you're the one who implemented this trick. The reader doesn't know this. So you have to tie it up in a nice, neat little bow at the end of it and tell the reader explicitly, like, yeah, you're looking at a mess of calculations here. If you're lost, don't worry. Here's my therefore statement. Therefore, all you need to know at the end of the day is that block A is traveling at 1.9 meters per second and block B is traveling at 4.9 meters per second. Okay, that's how you force an object to be at a velocity of 0 before the collision. And that's how you can always ensure that you can use those shortcut equations, and the derivation of which is provided in the notes. So we are just after the 1 o'clock mark. We are pretty much at the end of these. One thing I just want to say before I let you go, we're not going to do any questions. This is a fairly simple concept. I just want to put the idea in your head before I let you go. There's a notion of center of mass of an object, and you've all experienced this. A center of mass is the point at which you can pretend all of the mass of the object is located at. And you've all experienced this. It's how you balance things. So if you take an object, I'm going to use my iPhone here. If you take an object and you want to know where the center of mass is, you know, if you put your finger here, the iPhone will just fall. In fact, I'm going to temporarily stop sharing my screen for a second so you can kind of see what I'm doing here. So hopefully you can see I've got an object here in my hand. If I place my finger off center, obviously the phone will just fall. That's because it's not at the center of mass. If I try to place my finger at the center of the phone, I can balance my phone. And that's because the center of mass is the location at which you can pretend all of the mass particles in your shape, or sorry, in your object, are located. So you can pretend that all the mass particles are located at the center of mass. So that's how and it's easy to find in real life. You know, you just try to balance the object and you can find it. So I'll let you go with one idea in your head. You can mathematically find the location of the center of mass using this formula. Pretty much you're adding up a weighted sum, a weighted average, I guess, of the locations of all the masses. So the farther the mass is away, the more it contributes to the sum. The closer the mass is to the pivot, the less it contributes to offsetting the center of mass. We can worry about this later. When we do torque, we're going to come back to center of mass. What I do want to say, though, with center of mass is that the center of mass of a moving system of particles, so like we've been studying momentum, we've been talking about how a grenade explodes into 3 pieces. I do want to say, though, when you're studying conservation of momentum of a system of multiple particles, you can actually analyze the conservation of momentum of the center of mass of the system. This means if the grenade is one object and the grenade explodes into 3 objects, then the center of mass of the grenade must adhere to the physics of motion. So the center of mass of the grenade initially does not have a momentum, which means after the explosion, the center of mass of the grenade has to stay at the location it used to be. Similarly, if you throw a grenade, like you see in all the war movies, they pull the pin and then they throw it over their head and they shout, fire in the hole, and they duck or something like that. When they throw the grenade, that's projectile motion, right? You've got a single object with a grenade that is being thrown, and then halfway through the trajectory, it explodes into many pieces, 3 pieces, 4 pieces, however many pieces. Well, conservation of momentum still applies during the explosion, during the collision that is the explosion. However, if you want to know the trajectory of where all those pieces go, you can say, well, the center of mass of the grenade will follow the parabola. That's what we see here. The center of mass of a rotating baseball bat will follow a parabola in the same way that when you throw a baseball, you're going to get, a parabola. And again, if you don't believe me, we're all at home in quarantine right now. Take a stick, take a baseball bat. It's hot outside, so maybe wear some sunscreen and a hat. But go outside and maybe lightly toss a stick or a baseball kind of up as it rotates, and kind of watch how it still follows a parabolic arc. Even though there's other motion kind of happening, you can still see the sort of parabolic motion that occurs. Okay. That's all there is for momentum. As always, I've included the textbook's publisher slides. I don't think they're any more informative than what I've done, but they're there for you to look at if you want a second opinion. Okay, last lecture for the week. I'm going to call it quits soon for the recording. So if you're watching on YouTube at a later date, thanks for watching and making it to the end, and I'll see you on next week, next Monday.